Howdy, I'm Zeyu Mao. In this demo, I'm going to show network reconfiguration as cyber-physical mitigation in ResLab testbed. In the previous demos, we have already demonstrated modeling and simulating cyber-physical power systems, integrating real-world threat models, and integrating hardware field devices. In this demo, we would like to show the reconfiguration capability of communication network in the testbed, and show how we managed to have the real-time interactivity from both cyber and physical system. And last but not least, explore the possibility to utilize the cyber-side reconfigurability to mitigate adversary cyber-physical events. The basic idea behind network reconfiguration as cyber-physical mitigation can be classified as 3 steps: detection, exploration, and mitigation. For detection, we are using rule-based and inference-based intrusion detection system to detect the anomaly cyber-physical event. And then, based on the alert type and also the connectivity model of the cyber network, we are evaluating the possibility to use cyber-side action to mitigate the cyber-physical event and determine what is the best cyber-side action. For the current mitigation scheme, we are considering on-demand firewall update as well as rerouting. To validate this idea, we develop an interactive cyber-physical co-simulation on top of the ResLab platform. For power system, we are using Power Dynamics Studio to do the interactive electromechanical transient simulation. For cyber network, we are using Core for network emulation. Real-world penetration tools are also embedded into the Core. To make it more scalable, we also support meta-programming to convert graph model into the Core script. And we are using Helix to do the co-simulation in real time. This platform also supports hardware in the loop, not only for field device, but also for networking hardware, like L3 switch. In this demo, we are going to show how to protect the grid from cyber intrusion by reconfiguring the cyber network in this interactive cyber-physical testbed. 2 examples will be demonstrated. The first example is man-in-the-middle attack on control commands. In this example, we are using a 4-bus case, and the man-in-the-middle attack will happen on a main router at substation B, which causes the remote control commands cannot be executed properly by the field devices. To mitigate this, we are using firewall update to block the possible compromised ports. The second example is DOS attack, denial of service attack on AGC signal. For this example, we are using a WCC 9-bus case, and the DOS attack will be targeting the main router at substation B. As a result, the auto-generation control signals cannot reach generators at substation B and C, thus the system frequency cannot be stabilized. To mitigate this, we are using rerouting to ensure at least generators at substation C could receive AGC signal in a timely manner. For demo 1, first we will be running the DS Federate, which is a Python script to connect both DS, dynamic simulation, and Helix together. It uses DS protocol to connect and receive data from dynamic simulation. And Helix serves as a primary control network to connect the virtual nodes to the host network. The dynamic simulation is running in the host network. Once the DS Federate is initialized, we will be running the gRPC server script. The gRPC server script utilizes meta-programming to convert the graph model into the core script, and then using the core script to emulate the SCADA network. On the top on the right, you can see the graph represent the network topology. Once it's done, we will be running the gRPC SCADA script, which basically runs DNP3 outstations in the 3 nodes and DNP3 master in the main control center node. You can see now in the log section, there is DNP3 communication going on. The window just popped out on the left represents a HMI in the main control center, which receive data and display data from 3 substations. Generator, load, and branch status can be viewed in the HMI. This is the dynamic simulation we are using right now. To illustrate the interactivity of the system, I will issue an open command to one of the branch. As you can see here, in the DS, the branch is open. We could also issue a close command to put it back to service. As can be seen in the DS, the branch is reconnected. Now we will be running the gRPC adversary, which underneath will run the man-in-the-middle attack to perturb the normal DNP3 communication. Here it shows a Wireshark that is currently connecting to one of the router. Now, we will be using the HMI again to issue a close command to the same branch. Since the packet is adversarially modified, you can see now the branch is actually open. You could also observe the evidence of compromise in the Wireshark. To mitigate the situation, we will be running the gRPC monitoring and response script. The script will utilizing the alert from Snort and then update the firewall to block the possible intrusion. Now we will be using the HMI to send a new command to adjust the generator real power output at bus 4. As you can see, the command is correctly executed. Then we will also send a new close command to close the branch that is out of service. As you can see in the dynamic simulation, the branch is successfully closed. We could also observe that in the Wireshark, the DNP3 communication is back to normal. This means the firewall update is effective in this situation. For Demo 2, the first 3 steps are the same as Demo 1. The only difference here is this time we will be using the WSCC9 bus case. So first we will be running the DS Federate and also the gRPC server to enable both physical system simulation and the cyber system simulation. And then we will run the gRPC SCADA on all the virtual nodes. One difference here is this time the automatic generation control is enabled for all the generators in the case. Once the virtual nodes finish the initialization, you should be able to observe that the regular updates of the generation set points. Okay, now we will be running the gRPC adversary, which underneath will run the HPIN3 to execute a DOS attack on the main router 2 at substation B. Due to the DOS attack, the AGC signal cannot reach generators at substation B and C. Thus, the system frequency cannot be stabilized. To mitigate this, we will run the mitigation script to reroute the path from control center to substation C through substation A instead of substation B. As a result, generators at substation C could receive normal AGC signal.